So yeah, hey there, welcome back to another session of our CCNA training by PyNet Labs. And in this session, we're going to discuss about OSPF, Open Shortest Path First. As you already are aware about, in the last session, we discussed about Eigrp. And in this session, we are going to dig deeper into another routing protocol that we will use. So I hope I'm audible to you. Perfect. Let me just share my screen with you all so that we can move on. And there you go. I hope you all can see my screen now. All right. So to start with, we have seen now how RIP works, or Routing Information Protocol works, and how EIGRP works, right? So earlier we discussed about some of the methods that we can actually configure routing with, because we have been going through from the similar topology itself, that we saw how R1 and R2 and R3 can actually communicate together if we connect them in a network or so. But the protocols that we have used so far has been about RIP and EIGRP, and I'm talking about dynamic protocols and not static routing protocols. So static routing protocol is somewhat we have explored so far, okay? And then after that, we moved on to the dynamic routing protocol, in which we explored about routing information protocol and EIGRP in the last session. So we're going to move ahead and we are going to discuss something about OSPF, which actually stands for Open Shortest Path First. Now, almost every one of you might be familiar about what OSPF is and how OSPF actually works, but there are a lot of different factors as well in order to consider whether and how to use OSPF in a specific production environment and so on. So we're going to dig deeper into that itself, that how we can actually use it. Just a minute. So let's go ahead and see how OSPF works, and we'll discuss about some fundamentals of OSPF, and then we're going to see the implementation of how OSPF is actually OSPF works. So if we talk about some of the OSPF fundamentals, then you can say that OSPF again is an open source protocol, or you can say open standard protocol, or you can call it an open source protocol, where you can the source code of that OSPF is open for everyone, and people can actually use it for the networking devices that they want to connect their network with. So if you have a device of let's say a Cisco, and if you have a device that is not of Cisco, but you still can make them communicate with each other, and you still can make them exchange the routing tables that they have with the help of OSPF. Make sense? And if we talk about another, you can say property of that or characteristics of that, then OSPF is a completely linked state routing protocol, which means unlike EIGRP that considers multiple values or multiple factors in figuring out the best route, in figuring out the best way to reach out to the destination. Like if we talk about EIGRP, then EIGRP works with different K values, right? K1, K2, K3, K4 and K5. However, by default, only K1 and K3 is considered, which are basically bandwidth and which are delay in terms of figuring out what will be the metric. But if you change the K2, K3, K4 and K5 by default from 0 to either 1 or 2 or something else, then you can say factors like MTU, factors like load of that particular bandwidth, and factors like reliability will also be considered in order to figure out what is the best route in order to reach out to the destination. But OSPF doesn't consider all these factors. OSPF is a pure link state protocol where it takes all the decisions based on the bandwidth of that particular link. Okay, and that's why it is called as link state routing protocol. And EIGRP is called as advanced distance vector routing protocol because it takes decisions of how to forward that particular traffic with what route and so based on certain values that are available, in which by default only bandwidth and delay is considered. But over here in OSPF, it is pure link state protocol, as I told you, and it uses, or OSPF, however, I'd like to tell you that OSPF uses shortest path first algorithm, or you can call it as SPF algorithm. Okay, or you can also call it by the name that is called as Dijkstra algorithm. The official name of that algorithm that OSPF uses is called Dijkstra, but people also refer the calculation as shortest path first. So we call it either SPF algorithm or Dijkstra algorithm. Okay. Then, unlike other protocols like RIP and EIGRP, which provides you the ability to connect number of hops in your production environment, OSPF has a support of unlimited hop count. You don't need to really worry about how many hops do you actually need to connect together and how many hops you can say your router can actually communicate to. There's nothing that needs to be concerned about over here. Okay, so you can connect unlimited hops. Whether in RIP you can only connect 15 hops, and in EIGRP you can only connect around 255 hops. Make sense? But and by default as well, in EIGRP you only have 100 hops that are connected there. So that's one of the parameters that you need to be concerned about. Then if we talk about, yeah, this can be also said as the most preferred routing protocol in terms of being used because it has been open source since the beginning, and it has been open standard since the beginning. Unlike EIGRP, which became open source in 2013. Previous to that, EIGRP was a proprietary protocol which could also only be implemented into Cisco's devices. But now EIGRP can also be implemented into like other vendors' devices as well. But people have already adapted who uses devices that are not made by Juniper or who have a mix of infrastructure. They have been using OSPF for a long time, and nobody would look forward to actually change the entire routing protocol just because OSPF went public. Okay, so that's one of the parameter there, that OSPF is kind of the largest popular protocol for the IGP, for the interior gateway routing. Okay, or interior as an interior gateway protocol there. Good. Then the next characteristics you can say that is the AD value of OSPF is 110, 110. Make sense? The AD value of OSPF is 110, and unlike EIGRP, there is no internal or external AD. Like EIGRP has multiple ADs, right? It has 90 for internal and 170 for external. But OSPF only has a single AD, that is 110. Okay, and the metric. Now you are familiar that how metric is calculated. We have seen it in RIP as well, that the metric is based on the number of hops the destination is away, and in EIGRP the metric is calculated by considering the addition of bandwidth and delay and the product of 255. Okay, but over here the metric calculation is pretty easy. The metric calculation just uses a formula that says cost is equal to, or metric is equal to, 10 to the power 8 divided by the interface bandwidth. Okay, and 10 to the power 8 is basically nothing but 100 mbps. So if your link, or if your R1 is connected with a router called R2 and the link is of 100 mbps, okay, then in that case the cost of that particular thing will be 100 divided by 100, that becomes 1. Makes sense? If you're using a serial line to connect like these two routers together, then the link between that will be 1.54 mbps. So the formula over there will become 100 MB divided by 1.54, and that actually becomes somewhere around 65. So that's how the calculation would be done. So if you have R1 connected to R2 and then R2 again connected to R3 with a serial link, then the total bandwidth from here to here will be 65 plus 65. That will be somewhere around 130 or something like that, or 128 or something like that. Do you understand what I'm trying to say? That's exactly how metric is calculated in EIGRP. It's not that difficult, but yeah, this is what the formula is. So the 10 to the power 8, we call it as a reference bandwidth, and it is divided by the interface bandwidth. So reference bandwidth is always considered as 100 Mbps, okay, which is 10 to the power 8. And the interface bandwidth can be considered whatever that particular thing would be there. Sounds good? So these are certain parameters that we have in OSPF. Then after that, you can say that it is, of course, like all the features are there. You can consider that it is a complete classless routing protocol. Okay, which means just like RIP, EIGRP, OSPF also supports advertising the routes if they are of like subnetted, if the routes are subnetted like /27, /28 or something like that. Okay, then after that you can say that it supports, just like RIP and EIGRP, it supports VLSM and CIDR because of the nature that it supports uh, it supports classless routing as well. So that's why it also has the support of CIDR, which is classless interdomain routing. Then after that, it only supports equal cost load balancing. It only supports equal cost load balancing. What does it mean? You see, we talked about EIGRP and we saw something like that, like there was a characteristic that said EIGRP supports unequal cost load balancing as well, right? If you remember that. For example, if you have your R1 and if you have your R2 and if you have your R3 and if you have your R4, then there is another router called R5 that actually connects directly to R4. Now, in that case, both the routes will be making you reach out to the destination. And if you have another route, let's say you have R6 and you have R7, and then that R7 connects to R4. You understand that? Now, over here, you have three different paths, right? If I talk to you about that, this is path number 1, then this is path number 2, and this is path number 3. Your path 1 and path 2 might have a similar metric, which means they, let's say that they all reach out to the destination with a metric of 65. And then you have path number 3 that actually reaches out to the destination with the you can say 80 as its metric. So in that case, which route will be installed in your routing table? Obviously the route that has a lower metric will be winning that, but over there as well there is a tiebreaker, which means there are multiple routes that actually has similar metric, which is path number 1 and path number 2, and that's why this particular route will be inserted over there. However, if you want, in EIGRP, you can also make the third route, which has a greater, you can say, AD value there, or a metric there. You can also make that particular metric reach out to the destination, or get installed into the routing table. You understand what I'm trying to say? So OSPF only supports load balancing of equal cost, which means that if you want to install multiple routes into your routing table for the same destination, then the metric of that particular route needs to be same. Do you understand what I'm trying to say? All right. Then, after this particular characteristics, you also need to understand that just like EIGRP, OSPF also sends hello messages. We just discussed about how EIGRP actually works in terms of sending creating neighborship, but OSPF also sends hello message, and that particular hello messages goes out to, or you can say, the updates and hellos are sent to 224.0.0.5. This is the IP address, which is a multicast address on which the updates of OSPF are sent. Just like a RIP sends it on 224.0.0.9, then EIGRP sends it on 224.0.0.10, and OSPF sends it on 224.0.0.5. You need to take that into the consideration. Okay, these three are different IP address on which the dynamic routing protocol actually sends the updates on. Make sense? And it also works based on the triggered updates. Works on triggered updates, like EIGRP itself. It doesn't exchange the routing table every 30 seconds like REP. It is only going to send the update if there is any change in the network. And that's what we call as triggered updates, about which we have discussed in detail into the EIGRP section. Make sense? That's some of the characteristics. And then after that, as I told you, that it sends uh, hellos and updates and all on a specific address, but the hello also has a timer. So hello time in OSPF is 10 seconds, and dead time in OSPF is 40 seconds, which means that if, like, in order to maintain the link between the R1 and R2, both of these routers needs to exchange hello messages every 10 seconds. If the routers do not get hello message for 40 seconds, then they will kind of assume that the link is no longer up, and they will remove the routes that has been learned from that particular neighbor. Okay, and they will assume that the neighborship is broken down. You understand that? So that's what the timers are. These are, however, the default timers, and you can change those timers as well in EIGRP and in OSPF. Okay, but nobody really changes it, because you really need to be good. You really need to be good enough in order to understand that how these protocols actually works according to the timer. Make sense? Then it also introduces concept of areas for the better management, which means that just like we had autonomous system numbers in EIGRP, right? So in OSPF, you're going to have areas, different areas over here, which means if you have a couple of routers, like you have R1, then you have R2, then you have R3, and all of these are in, let's say, area 0. And then if you have R4, and then R5, and then R6, and all of these are in, let's say, area 10, then you can actually make different areas communicate with each other, but still they will be part of different area itself. Okay, Now we're going to talk about how these area systems actually work, okay, for the better management perspective, so that you can scale in a great manner possible by taking help of areas here. So I hope you understand that particular concept as well, that how areas actually work here. And there are different types of areas as well that are designated in terms of like creating the Ospf neighbor. So yeah, that's one of the things that it introduces the concept of areas for the better management purpose. Okay, and yeah, you can say these are different uh, characteristics of how Ospf actually works, and I hope you understand all of these characteristics. Pretty basic one. Any questions there? Great. Now, what we're gonna see is we're gonna discuss about how OSPF actually builds up the neighborship, just like what we discussed in EIGRP, that how EIGRP neighborship is built. We are going to talk about how OSPF neighborship is built over here now. Okay, so for that, I'm gonna take again the same router. Let's say we have R1 here, then we have an R2 here, and we are discussing about OSPF neighborship process. Good. So in this OSPF neighborship process, you have this R1 and you have that R2, and both of them are connected with this 12.0.0/24, where dot 1 is here and dot 2 is here. Make sense? As soon as you configure OSPF onto the routers, then the thing is going to be same here. But there are certain OSPF stages that you actually need to know. So when the OSPF is just configured and there is no network that has been advertised, then there is a state of the OSPF which is called as down state. And as you turn on the interface and advertise the networks, then that particular state changes from down to something called init, that OSPF has been initiated. Make sense? And once it reaches out into the init state, then both the routers will start sending the traffic. Okay, they will say hello on a multicast address that's going to be 224.0.0.5. And then R2 is also going to send hello message saying 224.0.0.5. And just like EIGRP as well, there are certain OSPF neighborship parameters as well that actually needs to be matched. So the first parameter over here is that both the routers needs to be again in same subnet. Okay, then the second parameter is their area number that you're going to configure also needs to be same. So they should be member of same area. And then the third parameter over there is they should also have same hello and dead timer. You understand that? In EIGRP, the third parameter is that they should have same K values. But there is no concept of K values in OSPF. That's why it considers that the timers, which are hello and dead timer, needs to be same on both the sides. And this is not a criteria in EIGRP. You can have different timers in your EIGRP and still you can become neighbor. But that's not going to happen in OSPF. Do you understand that? So after matching these, you can say parameters, then you will become neighbors. And then OSPF also maintains something called OSPF tables. And the very first table is of course called neighbor table. And the information about that neighbor is going to be installed into the neighbor table of the OSPF. Make sense? And then the state will be called as something like two-way state. It means that the exchange of the hello packets are done and now the neighborship has been formed. Okay, so you will become in two-way state. Then the next state is basically called as X start, which means they need to start the exchange of the routing table, because both of the routers must have advertised some of the networks, and these networks needs to be exchanged between the OSP of neighbors. Now the question over here is, who will do the exchange first? Okay, is it gonna be, is it like, is R1 going to send the update first, or is R2 going to send the update first? And this particular thing is actually decided by something that is called as let's say, just a minute. So this is something that is actually decided by a thing called router ID. Okay, now what is this router ID? So there are certain priorities that how router ID can be figured out, and there is, you can say, there will always be a router ID configured for a router that actually participates in OSPF. Okay, so the first priority is given to manual router ID. It can also be configured manually, so you can have a manual router ID there. If the router ID is not configured manually onto the router, then the router will automatically choose the router ID, and it will give the second preference to the highest loopback interface IP, or the highest loopback IP. And even if there is no loopback that is configured onto the router, then the third priority will be given to the highest active physical IP. You understand that? Which means that, consider that there is a router which has this as an interface, this as an interface, and this as an interface. And you have an IP address of 10.1.1.1, which is FA0/0. Then you have 172.16.0.1, which is loopback 10. And then you have 192.168.1.1, which is FA1/0. So for this router, what is going to be the router ID? Can you guess that? Yeah, of course. So the highest, because there is no manually configured router ID on that R1 available, right? So for the same, the second priority will be given to the highest loopback. Now, even though the physical IP address over there has the highest IP configured amongst all of them, but the second priority is given to the loopback interface. Okay, and that's why 172.16.0.1 becomes the router ID of that particular router. And it doesn't really matter whether you have advertised that particular network into the OSPF domain or not. It is possible that you are not using that particular network into the OSPF domain, but still your router ID will be configured, or your router ID will be assumed, which is the loopback interface IP address. Make sense? So that's how router ID is actually considered there. And we, however, in our topology are going to configure the router ID manually, so no need to worry about that now. But yeah, if we look at the topology that we have, then R1 and R2, both of them have the both of them have the IP address, which is 12.0.0.1 and 12.0.0.2. Okay. And if you look at that, then 12.0.0.2 becomes the highest active physical IP address. And that's why R2 is going to be the one who will actually initiate the routing update. Make sense? So loopback interface, as I told you, that it's just a normal interface that we're going to see how we can configure that loopback interface. Okay, it's just like a physical interface, but it physically doesn't exist. So you can go onto that particular router, you can just say interface loopback 10, and a new virtual loopback interface will be created, and you can assign it an IP address. Okay. So that particular IP address can be verified by running a do show IP interface brief command into your router, and that should solve your purpose. And then over here, if you look at X star, then based on the router ID, because R2 has a higher router ID, router IP address, that's why it's going to become the router ID of choice. And then R2 is going to exchange the routing table by saying, here is my routing table, right? And then R1 will basically give an acknowledgement to that, and R1 will exchange its routing table as well, saying here is my routing table, and then R2 will basically acknowledge to that as well. You understand that? Now, here is a major difference between EIGRP and OSPF. We saw how EIGRP and OSPF actually differs in a way of how they exchange the routes or the number of routes that are available into the topology. Okay, so assume that you again have R1, and then you have R2, and then you have R3, and then you have R4, and then you just want to reach out to R5. And as I told you in the yesterday's example, that R2 has around 2 routes, R3 has around 3 routes, and R4 has around 5 routes. And these are basically OSPF neighbors. Okay, so when we consider them as OSPF neighbors, then in EIGRP, the neighbors will just give their best route that is available to the destination. But OSPF neighbors will give all the route that they know about. So R2 is going to give the 2 routes, R3 is going to give the 3 routes that it knows about, and R4 again is going to provide the 5 routes that it knows about to reach out to the destination. They are not going to give only the best route, but they are going to give all the routes to the neighbor. And these routes are basically going to be inserted into the second table of OSPF, which is called as database table. Make sense? So this route is going to be established or is going to be stored into the database table, and then the calculation will be done, and the state will actually be called something as loading. Okay, no. The state will actually be called something as exchange, which means the routing table has been exchanged when the routes are placed into the database table. And then the next stage is going to be something called loading. And what do we mean by loading? Loading means the process of selecting the best route from the total available routes into the database table, and then placing the best route that is available into the routing table or route table. So there are going to be almost 10 routes into the database table, and out of that 10, only one route will be going into the routing table. And that process is basically done in the loading state. And once it is done, then your topology reach out to a state called full. Okay, so when it reaches out to the full, it means that the network has been converged, and you can actually send data to the neighbors or through the neighbors to the destination network that is available. Do you understand how it works? So this full is going to have that routing table over there. Make sense? Perfect. So this is how OSPF actually works, okay? And we will see it in action now by configuring it, okay, and seeing how it's gonna work there. So let me design a quick topology for ourselves, and we will see how it actually works. So I'll clear this thing up, and then I'm gonna have a couple of routers with us, and we are just gonna build up a small topology like we did yesterday. In that we're gonna have a couple of switches, and then we're gonna have a couple of PCs. like that. There you go. Then you can actually name it as 192.168.1.0/24. You can name it as 192.168.2.0/24, and you can name it as 192.168.3.0/24, just a common thing there. And then we will open up each and every router and we will configure the IP address parameters in just a minute. So I'm going to click on R1 and going into the CLI. This is the CLI for R1. I'm going to say no. Enable conf hostname R1. Then interface FA0/0. No shutdown. IP address 192.168.1.1 along with the subnet mask. And then IP DHCP pool A network 192.168.1.0 along with the subnet mask and default route or default gateway 192.168.1.1. Makes sense? Then we're going to change that particular interface to SE2/0. We're going to say no shutdown and IP address 192.168.3.1 along with the subnet mask. You get that? And then that's all actually that we need to do for the IP configuration. We can go onto the PCs and we can check whether we have received the IP addresses via DHCP. And there you go, it's working fine. We can close this PC, we can go on to the next PC and fetch out the IP address via DHCP. Requesting. There you go. And then after that, we can go on to the next router and configure the things. So I'll close down this particular PC, open up the next router, go to the CLI, say no, enable configure terminal, then interface FA0/0, no shutdown, IP address 192.168.2.1 along with the subnet mask and IP DHCP pool B and then network 192.168.2.0 along with the subnet mask and default router 192.168.2.1 and take an exit there and then go to interface SE2/0 no shutdown IP address 192.168.3.2 along with the subnet mask. Okay, and we can now then change the name of that particular router to R2. So that is all that we actually had to do for the IP configuration purposes. You can see that the topology is all green. And you can go on to each and every PC and fetch out the IP address with the help of DHCP. So go to desktop and IP configuration and DHCP. And then you can see do 2.2. Then I can close this particular PC, go to the next one, and desktop and IP config and DHCP. And there you go. The DHCP request has been configured successfully. Now the only thing that is left, because when I go onto that particular router and if I check the routing table, of course you guys know now that the routing table is only going to show us the directly connected network, that is 1.0 and 3.0, and same happens over here as well. If I say do show IP route, it's going to show me 2.0 and 3.0. So in order to make these computers communicate with each other, we need to create an Ospf domain there, okay? And we're gonna specify there that we are gonna use area number 10, okay, over here. And we can actually also, we're gonna create a topological help for ourselves. Yeah, we can see it like right. There you go. Like this. Yep, and we can place this area 10 here. So you understand that this is area number 10. Make sense? Now, in order to create this, the only commands that we're gonna use over here is go to router. Then just like OSPF, we're gonna use a command that says router OSPF. And then after that, you also need to use something which is called as process ID. So this process ID is not the area ID, by the way. The process ID is a local value that actually used, which is locally independent or locally, it's for the local significance. Okay, as there can be multiple processes that your router can handle, but in order to identify each and every process, you need to use a process ID. So this is not the area ID that actually needs to be matched, which is one of the parameter for creating an Ospf neighborship. This can be anything. So I'm just giving over here, according to the name of the router, that router Ospf1. Okay, and then inside of that, I'm going to specify my router ID with the command that says router-id. And I'm going to say router ID is 1111. It needs to be in the form of an IP address itself. You see a.b.c.d. So router ID of the OSPF in the IP address format. So I can use anything. I'm just going to use the router name here that says 1.1.1.1. And then after that, I am going to advertise my network with the help of network command. Okay, but over here we specify 192.168.1.0, which is the directly connected network that we have. Now here's the trick, okay, or here's what is different than RIP and EIGRP. In RIP and EIGRP, we didn't use to mention anything. We could directly advertise our network just by using the network ID of that particular network. But here, you need to use a term or you need to use something that is called as OSPF wildcard bits. Now, what is this wildcard bits? Okay, so if I tell you the wildcard bits actually is when you look at this wildcard mask or wildcard bits, it is something called inverse of subnet mask. Okay, it is actually the inverse of subnet mask, which means if your subnet mask is 255.255.255.0, then your wildcard mask is going to be 0.0.0.255. Do you understand that? Which means that if I write down it even in a better manner, let's say that your wildcard mask is 255, 255, 255.0. What is going to be the binary of this particular subnet mask? It's gonna be 1111111 dot 1111111 dot another set of 1 dot a set of 0. That's what your subnet mask will be. Then based on that subnet mask, what will be your wildcard mask? So your wildcard mask becomes 0000 dot another set of 0 dot another set of 0 dot the last set will convert from 0 to 1. You understand that? And based on this, then you can actually convert it to 0.0.0.255. So if your subnet mask has 255, that will convert to 0. If your mask has 0, that will basically convert to 255. Make sense? This is how you figure out the wildcard mask or the wildcard bits. And this wildcard bits is also going to help you to be able to configure access control list, which we're going to discuss into the security section of our course. Okay, but yeah, it is kind of a syntax that you can say there is no logic behind it. However, when you will study OSPF and CCNP, then you will get to know that why do we actually need this wildcard bits over here. Okay, but there is no use of wildcard bits to be understood in the CCNA level, of course, in for the section of OSPF. And you cannot use subnet mask here. If you even mention 255.255.255.0, then in that case it will treat it as the wildcard mask itself. So over here, yeah, if I take another, you can say example. Yeah, let me just erase this. So if I take another example of how this thing will work if you have a subnet that is not a default subnet but of a different subnet. So in that case, let's say you have 255.255.255.224. Okay, then what will be the wildcard mask of this? It will be 000 dot. What you need to do is you need to subtract the value that you have here from 255. So 255 minus 224, it becomes 31. You understand that? That's how the wildcard mask is going to be here. Cool. So this is how wildcard mask can actually be understood. And then in order to use it over here, what we're gonna say, network space 192.168.1.0 space 0.0.0.255, and then after that we need to specify area and then the area ID. So the area ID can be anything. Okay, it can be anything from 0 to almost that particular value that you see. Okay, so I'm going to specify over here that the area is going to be 10. And then I'm going to advertise, and this is exactly how you advertise your network in OSPF. Then I'm going to advertise my next network, which is 192.168.3.0, along with the wildcard mask and the area number as 10. And that is done. Okay, this is all that you actually need to do in OSPF advertisement. Then I'm going to go on to the second router, and then after that I can go on to this particular router and I can say router OSPF. Now over here I'm going to use it too. Okay, and then I can say router ID is 2.2.2.2, and then I can say network space 192.168.2.0 space 0.0.0.255 and area 10. Okay, the area number needs to be same over here, doesn't matter what the process ID you use. And then after that I can advertise my another network, which is 192.168.2.0.0.0.255 and area 10. And as soon as I do that, the Ospf neighborship, oh, okay, sorry, that's my mistake there. I need to use another one, which is 3. I advertised 2 and 2 again, so that's kind of a problem. Yeah, the next network is going to be 3, and as soon as I do that, there you go. This is your OSPF neighbors adjacency. Okay, it says the process number 2, neighbor 1111 has came up. This is the router ID by which your neighbor is going to be identified with, and it says process done from loading to full, which means that the route has been installed into your routing table, and you can check that by using do show IP route. And there you go. There's your OSPF route there. You get that? And the AD value for this particular route is 110, and the metric is 65 because we are using serial link, which has a speed of 1.54 Mbps. Okay, so according to the formula, it gets divided there, and then it says the route has been learned via this route, and it's been 21 seconds since it learned the route. Okay, and the route is going to stay there. There is not going to be any new update that will come up there until unless there is any change. So this particular route will stay there for a longer time. Okay, unlike RIP that exchange or that resets the timer every 30 seconds that it receives the new update. So OSPF also works on the basis of triggered updates, and that's how it's going to help you. Make sense? Yeah, so go ahead and try this particular lab and see if it works for you. Okay, and I'll catch you guys in some time. Okay, take your time, do this particular lab, and yeah, let me know when you're done. Thank you. Yeah. Sorry, I just went to the restroom. Yeah. Over here. This is the topology. I've used router ID as 1.1.1.1. And for the second router, I've used the router ID as 2.2.2.2. Yeah. Hey there, I am back. Let's move on with the next thing. I hope you can hear me and I hope you can see my screen. Perfect. Now so in this section, we are going to discuss about the advancements of OSPF and how it actually works. So we'll first investigate different tables that are available in OSPF, like we talked about neighbor table, we talked about the database table, and we talked about routing table as well. So these tables can actually be viewed over here by using commands like enable conf t and saying do show IP OSPF neighbors. And when you use that, you will see that the neighbor ID is 2.2.2.2, right? Then you see the state over there, the dead time there, then the address there. You see, so how it works is the dead time actually spans from 40 to 31, 40 to 31, and every time it receives a new hello, every 10 seconds it restarts or it goes back to 40 seconds. So the counter resets to 40 and it again starts till 31, 36, 34, 33, 32, 30. You receive a new hello, again starts from 40. Make sense what I'm talking about? So if this particular dead time reaches out to 00 from 40, it means that it's been 40 seconds that your link has not received or your router have not received the hello message from the neighbor, and then the neighborship will go down. You understand that? So the hello time and dead time is there in order to help you to understand how it actually works there. And you can see that your neighbor is being identified with router ID 2.2.2.2. Okay, and the address over there is 192.168.3.2 as well, which is the neighbor's interface address with which you are connected. Then you can also check the routing or the database table that's there, which can be viewed by saying do show IP OSP of database. And this is the database that you have. Okay. Now, to study OSP of database, it is not that easy as compared to the database, or you can say link of Eigrp's topology table. OSPF's database table is quite difficult to understand. Okay, and this is something that you will learn in CCNP when you will investigate OSPF in a deeper manner there, because there are a lot of aspects that are available. You need to learn about LSU, you need to learn about LSR, you need to learn about link state advertisements and so. But yeah, you can get to know about that you can check the OSPF database like this. Okay. Then after that, you can just yeah, in order to get to know about it, then you can perform do show IP route here. And in the do show IP route, you will see a route there that actually specifies. If you just want to check the OSPF routes, then you can perform a command like this as well, do show IP OSPF route. And it will only show you do show IP. Oh, sorry. So what you can do is show IP OSPF, and then okay, that's something that is available for Eigrp, not OSPF. But yeah, in order to check the routing table, you can perform show IP route directly there, and you will see that the route is present over there with the OSPF thing. Make sense? So these are different, I would say, tables that are available with which you can get to know about the information. And then after that, the major thing that you need to understand over here is how the router ID works. So you see, if I use, or if I'm using my router ID over here, that says actually, or that is actually 1.1.1.1 here. And then my router ID is 2.2.2.2. Okay. In that particular scenario, what happens is, if and only if the router ID do not matches with each other, then and then only they will become neighbors. Because what happens, the routers store the information about their neighbors with the name of the router ID itself. Okay, as I showed you that, you can check over here, show IP Ospf neighbor. There you go, 2222. So you or the router is not storing the information about the neighbor with the help of some IP address or so, however, that contains the information about that IP, but it identifies the neighbor with the help of the router ID itself. Okay, and when if you end up configuring the router ID that is same there, like instead of using 2222, you are also using over here 1.1.1.1, then this kind of becomes a mismatch there, which means the router ID are not different, and that's why it gets hard for that to identify how your router ID is being performed. Make sense? So that's why you need to keep the router ID different, and I hope that makes sense to you. Yeah, yeah. As so I was saying, yeah, over here, if you want to check just the OSPF route, the command I believe is not show IP OSPF route; it's show IP route OSPF as mentioned. Yeah. So this is the routing table for the specific OSPF route that you can learn. Sounds good. So that's basic characteristics. Now another factor that we actually need to understand over here is how OSPF areas work. The most important thing over here is OSPF areas. So when we talk about OSPF areas, then there are, I would say, two type of areas that we have, or three type of areas. Yeah. The first type of area that you have is normal area, and the second type of area that you have is called as backbone area. What is this normal area and what is this backbone area? In order to understand this normal and backbone area, when I say that my R1 and my R2 is participating in common areas, be it 10, be it 20, be it 30, be it any number. And the number can be actually anything between a given range. But when we talk about it, you can understand that if I have a router over here, and then if I have a router over here as well, and possible that I have advertised my route as part of area 10, and then I have advertised my route as part of area 20 on R2. So do you see that the network that is actually being advertised on R1 and R2 are part of different areas there? So what would happen in that case? In this scenario, then the routers will not be able to communicate with each other because they are participating into different areas. Make sense? If I'm using, and usually this particular backbone area there is called as area 0. Area 0 is dedicated as something called backbone area. Okay, and normal area is anything except area 0. So all your area 1, 2, 3, 4, 5, 6, 10, 20, 30, whatever you get, it's all area, it's all like a normal area. It's treated like a normal area. And your normal areas cannot communicate together until unless they are directly or indirectly connected with backbone area. Do you understand what I'm trying to say here? I'll explain that again to you. So consider one more thing here, that instead of having this topology, let's say something like this. So you have your R1, and then you have your R2, and then you have your R3 and your R4 connected with it, and then you have your R5 and R6. This is your topology. Now let's say that the network that you're using over here is 12.0.0.0. Oops, sorry about that. I'll again draw that. R3 has R4. Just a minute, guys. Yeah. So as I was talking about that, if you have your R1 and then you have your R2 connected there, and with that you have R3 and R4 connected, with which you have your R5 and R6. This is your topology that you have. Now in this case, let's consider that R1 and R2 has a network of 12,000. R1 and R3 has a network of 13,000. R2 and R4 has a network which is common between 24,000, and R3, R5 has 35,000, and R4 and R6 has 46,000. Okay, and every router over there has certain, you can say, fast Ethernet network that is connected with them. So if I take a scenario in which R1 and R2 are sharing a common area, which is area 0, then the networks which actually will be advertised into the area 0 will be able to communicate together. Do you have any question over here? I think you're good over there, right? That whenever you advertise a network in a common network, in a common area, that particular networks will be able to communicate together. Then after that, consider that this R3 is actually participating into another area. Let's say that is area number 10. Okay. And then this R4 is also participating in another area. Let's call it an area number. Okay. Sorry about that. Yeah. So this R4 is participating in area number, you can say 20. So R1 is in 10 and R2, R3 and R5 are advertising their networks into area number 10, and R4 and R6 is actually participating into, or actually advertising the networks into area number 20. And then there is another link over here. So will A10 or will area 10 and area 20, would they be able to communicate together? They will not be able to communicate together, right? Now in that case, what would happen if I create another link and I connect them with that particular link like this? Now if I connect this R3 with R4, what would happen in that case? Will they be able to communicate together? In that case as well, they won't be able to communicate. So the common matter over here, or the common factor over here, is that your different areas, understand this pretty well, different areas can only communicate when they are directly or indirectly connected to area 0. You understand that? It means that different areas can only communicate when they are directly or indirectly connected to area 0. For example, if I create a scenario in which that I have a router that actually advertises all of its routes into, like, it has around 3 networks. Okay, this is 10, that's 20, that's 30, and that particular router is connected with another router which is R2 with 20 network, and then your R3 is over here that actually has a network called 40. Now, as a matter of fact over here, both of this 10 network is actually advertised in area 0. You understand that? And then this 20 network is advertised in area number 10. Now tell me one thing, that will this R2 be able to communicate to a network called 40? It will be able to communicate with the network that is connected to R3. Makes sense? 40 is basically a network that's 40,000. And why is that? Because it will be able to communicate with it because R2 is trying to communicate with 40.0, but it will be able to communicate there because R2 is connected to a network which is also a part of an area or a router that participates in area 0, which means that different area 10 and area 0 can communicate only because area 10 is connected to a router which also is a part of area 0. Quite complicated it is, but yeah, you need to understand it in a way that whenever you have a network that is advertised in not in backbone area, not in area 0, but your router is able to communicate with a router who has advertised that particular router's networks into area 0. So as R2 can communicate with R1, right? Do you understand that? R2 doesn't have any area, route advertised in area 0, but R2 can communicate with area with router 1. Do you understand that? R2 can communicate with R1, and R1 has one of its network advertised in area 0. Makes sense? That's why it will be able to communicate with any area that is connected or in any area that is advertised in the area 0. Make sense? This is actually how it works here. And now let's say, as we can take an example, let's say there is another router that's called R4, and that R4 has another area called area number 20. You get that? So in that case, R4 is connected to a router which is not majorly a part of R3 there. So for that reason only, R4 will not be able to communicate with R3 because R4 is not connected to either area 0 or also it is not connected to any router that actually has advertised their route into the router 0 or into the area 0. Make sense? So every single router needs to have direct or indirect connection with area 0 in order to make the network advertise or in order to make the area communicate with that particular router. Make sense? You'll understand it in a better way when I execute this scenario. Okay, so let's go and see how it will kind of affect in a real-time topological scenario. So what I'll do, I'll kind of remove, I will kind of, yeah, let's say, I will delete this, or you can say, I will change this to area 0. Now instead of this, we can do one thing. That I'm going to remove the routes that are advertised in area 10 and 20. Okay, so on R1 you can see that show IP route. or do show IP route. And you can see over here that when I perform do show run to check the running configuration, you can check your router OSPF configuration that I've advertised both the routes 1.0 and 3.0 into area 10. Now what I'm going to do is I am going to advertise, because if I check now if my PCs or if my device will be able to communicate with the other devices that are situated there, then you can see I select a packet, send traffic from here to here. The first packet will be failed and then it will go successful. If I try to send traffic from here to here, it will be fail and then successful. So the communication is working between area 10 as of now. This is area number 10. However, I have renamed it to area 0, but it is area number 10. Now what I'm gonna do, I'm gonna add another router. And in that particular router, I'm gonna advertise that network. I'm gonna add this router, then I will add another switch there, and then I will add another PC there, and then the connectivity. You get that? And this particular router is going to participate into something called cool. So this is still your area number 10. And then this over here becomes your area number 20. Good. Now over here, the network that we're gonna have, again, I'm gonna give it as 192.168.5.0/24, and then I will give it as 192.168.6.0/24. Okay, 192.168.5.0 and 192.168.6.0 in that case. So I'm going to build up this IP configuration here and see how it works. So I'm going to go on to the R3, go to the CLI, say no, enable conf interface FA0/0, no shutdown, IP address 192.168.3.1. Oh no, we're going to have 6.1, right? Then IPDSCP pool B or C and network 192.168.6.0 along with the subnet mask, and then default router of 192.168.6.1, and then we take an exit there, go to interface SE2/0, no shutdown, and say IP address 192.168.5.2 along with the subnet mask and take an exit. Right? If you go and check, we have 6.1 configured on the FA0/0 and we have 5.2 configured on the SE2/0. And I'm just going to add 5.1 onto the SE3/0 of this R2. So I'm going to go on that, say enable conf interface SE3/0, no shutdown, and then IP address 192.168.5.2 along with that. Oh, sorry, it needs to be 5.1 here, right? Otherwise, there will be same IP address. So that's how the IP config is. So we have now 3.2 and 5.1 there. And then we have 192.168.6.1 and 5.2 there. Now what I'm going to do is I'm going to advertise both the routes, which is 6.0 and 5.0 on R3 as a part of area 20. Okay. So I'll go over here, I'll say host name is R3, router OSPF 3, let's say, router ID 3.3.3.3, and then I'd say network 192.168.5.0.0.0.255, area 20, and then I will also advertise this as 6.0, area 20. Okay, then after advertising both the networks into area number 20, I'm going to advertise 5.0 of this particular router into the same OSPF process but in different area. So if I check the current configuration and if I say do show run pipe section router OSPF, it will just show me the running configuration of the OSPF. There you go. So I'm using process number 2, okay, and I'll go in that particular process saying router OSPF 2, and then I would say network 192.168.5.0.0.0.255, area 20. And now if I check, you see a new neighbor adjacency has been formed, and you can verify that by saying do show IP OSPF neighbor, that there a router an area is a neighbor is 1111 and there is another neighbor called 3333. You get that? And then in that particular case, this particular router, which is R3, also has a neighbor. Do show IP OSPF neighbor. There you go. 2222. Make sense? Now if I go on R2 and if I check that, do show IP route. This particular router has the knowledge of 1.0, which is basically a route that has been received from R1, right? And it also has a route that's called 6.0, which is received from a router called R3. But R1 is connected with R2 via area number 10. And R3 is connected with R2 via area number 20. So if I go and try to communicate with here and here, let's see what happens. IP config. I'll get the IP addresses on these PCs. There you go. And on to the other PC, desktop, IP config, and DHCP. There you go. The IP is configured, and if I go and check now, and if I try to send traffic from here to here, the first packet failed, second also failed, so failed. You see, it's being failed. And why is that? Because when I go into R2 and if I check that, do show IP route, do show run section router OSPF, then you can check that the route, which is 192.168.2.0, which is actually the route over here. I have advertised this particular route as area number 10. Make sense? And I have not advertised that particular route as area number 20. So even though the router has the information about the source network and about the destination network, even then as well, the traffic is not being forwarded onto that particular destination network. Why is that? Because that route is not part of that particular area. Now what happens if I do something like this? If I try to ping directly from the router by saying do ping 192.168.6.2, then I'm able to ping from the router to the end PC. So from here to here the communication is working, but from PC to PC the communication is not working. Okay, now what happens? So if I kind of go ahead and if I add another network here with that particular router, let's say I add a switch there 2960 and I add a PC there. I'll just add a single PC here, and then if I try to connect with that particular PC. Okay, and then let's say I create a network 192.168.7.0/24. Okay, and in that scenario, I provide the IP addressing scheme to that. So this is 7.0 here. So I go on to the R2 and I configure FA1/0 with that thing. This is R2 interface FA1/0, no shutdown, IP address 192.168.7.1 along with 255.255.255.0 IP DHCP pool. Let's say B there, or sorry, C there, network 192.168.7.0 along with 255.255.255.0 default 192.168.7.1 and take an exit. Okay, then I'll go on to the PC. That's fine. I can have the pool number C as well because C is here and C is here. So locally, that's again local significance. So I go on to the PC and then desktop and then go to DHCP. There you go. DHCP request successful. So you can check that it's working there. And now what I'm gonna do is I am going to advertise my newly created network as a member of area number 20. So I say router OSPF, what that thing was. So I say do show run section router OSPF. Yeah, OSPF number 2. So I say router OSPF 2 and then say network 192.168. 7 or yeah 7.0 and the wildcard mask will be 000.255 and area number 20. When I advertise this route, you can check that there is a new route that has been advertised now, and after that do show IP OSPF neighbor or do show IP OSPF or do show IP route. There is no change into the local route. There is just a new directly connected route that has been added. But if I now check my other router, which is R3, do show IP route, then you have a new route that has been added, which is 7.0. Makes sense? But whatever route on, be it on, or whatever routes that are there, which are advertised as member of area number 10, okay, be it like 2.0 or be it 3.0 or be it even 1.0, those routes are not exchanged to R3 because R3 is not participating into that particular area, but R2 is participating in area number 10 and also in area number 20. That's why when I try to send traffic from here to here, the first packet will fail. There you go, successful. The ARP was already done there. Makes sense? So the communication between here and here is possible. And the communication between here and here is also possible. You understand that? And that's how normal areas actually behave with each other. Okay? This is all normal area. We're not talking about backbone area yet. Cool. So that's kind of an understanding of how normal areas actually work. You cannot make different areas, be it area 10, 20, 30, 40. They cannot actually communicate with each other, even though you have advertised the traffic, you have advertised the network under the same OSPF process. Okay, yeah. Somewhat like VLAN, but not completely like VLAN. There is a bunch of other things that are available in OSPF that you will learn in professional studies. But yeah, this is just an overview of how areas actually work. So go ahead, try this particular thing, and then after that, we'll see how backbone area comes into play in that particular scenario. Okay, try this lab and let me know when you're done. Hey there, I'm back. So in this section, we're going to discuss about the area 0 and its characteristics, that how it can actually communicate when you make it part of area 0 or so. So what we are going to do here now is we're going to create another network in our scenario, and we are kind of going to make this area 10 and area 20 communicate with each other. Okay, and I'll show you how you can actually do that. So I'm going to drag this particular topology down, and we are going to create another sort of network there by placing a router. Let's say I drag a router there, and then in that particular router, what I do is connect those routers with something like this. Okay, I take a cable there and connect it with this, and I take another cable and connect it there. You get that? Now over here you can see that the network that we are going to create in that particular scenario is that you can actually get rid of this network which you have here. So what I'm gonna do, I'm gonna delete this network completely, and I will also delete this router here. Make sense? And I will also delete this area and this area. So we don't have these networks anymore, and we just have this plain network. And in this scenario, we are going to create a network which is 192.168.1.0 is here, 192.168.6.0 is here, and then we're going to create another network. Let's say the network between this is going to be 192.168.2.0/24 and 192.168.3.0/24. Okay, that's how the network is going to be. So what I'll do, I'll remove the Ospf configuration from this router and from this router. So I'm gonna go onto this router here, say enable conf, and I can check do show run section router Ospf. We are running router Ospf1 here. So we say no router Ospf1, and you can check do show IP Ospf, oh sorry, do show run section router Ospf. There you go, nothing's there. Same way, we're going to remove the Ospf configuration from the other router that we have. Enable conf do show run section router Ospf. There you go, no Ospf running. So there's Ospf process 3. So I'll say no router Ospf 3. And that's how you make it clean. So as of now, there is no Ospf configuration that is done in any of our router. There is just IP configuration that has been done, out of which we are not using SE2/0, but our SE2/0 is configured with 5.2. So I'm going to remove that particular configuration from there, and I'm going to keep the 6.0 configuration because we still have that network in our scenario. You get that? So for removing the configuration of SE2/0, I can simply go to conf and I can use a command called default space SE2/0 or default interface SE2/0. So it brings down the configuration to the default configuration itself. Okay. So when I say default interface SE2/0, what it does, it removes all the configuration that you've done. There you go. SE2/0 is now went to state down, and then there is no IP address that is configured. You get that? Just like that, I'm going on to the first router as well, and there we have SE2/0 as well configured. I'm also going to remove that particular configuration from there. Okay, yeah, it will work to FA0/0 interface, big interface, any interface that's there. So I'm gonna go on my R1 and I'm gonna say default interface SE2/0, and there you go. We have removed the configuration of that particular interface as well. And now we're gonna configure our serial interfaces that we have. So I'm gonna go on R1 and configure 2.1 here, 2.2 here, 3.1 here, and 3.2 here. So that's my R1 config interface SE3/0, no shutdown, IP address 192.168.3.1. Oh, that's 2.1, I believe. Yeah, 2.1, and then this subnet mask. There you go. SE3/0 has been configured with 2.1. Then I'm gonna go on to the next router, which is R3, and configure it with 3.2 on the SE3/0. So that's our R3 interface SE3/0, no shutdown, IP address 192.168.3.2, space 255.255.255.0. Just a minute, guys. I will probably need to put my iPad on charge. Give me a minute, okay? All right, I'm back. So we have configured IP address 3.2 on our R3's interface that is connected over there. And then we will name this router as R2, and we are going to make this particular router as a member of area 0. So I'm going to go and configure 2.2 and 3.1 over here. Okay, or yeah, 2.2 and 3.1. Let's first check. Yeah, 2.1 is here and 3.2. Okay. So I'm going to go on this router and configure it with the dedicated or desired IP addresses. I'm going to say enable config hostname R2 interface SE2/0, no shutdown, IP address 192.168.2.2 along with the subnet mask, and then interface SE3/0, no shutdown, with IP address 192.168.3.1 along with the subnet mask, and exit. And there you go. The links are up and the IP or the topology is working all good. Now we're gonna make the partitions in a way that how the areas will actually be working here. So I'm gonna select the color for our area 0. That's gonna be our area 0. And then we're gonna have our area 10, which is this, and then we're gonna have our area 20, which is this. Okay, so that's our So that's our area 20. This is our area 10, and that is our area number 0. Sounds good? Now we just need to go into every area and we need to advertise the network for a dedicated area number that we have. So I'm going to go on R1, then I'm going to create an area process number 1, and advertise 2.0 into area 0 and 1.0 into area number 10. Make sense? For that, I open up our for that I open up our R1 and I say router OSPF1 router ID 1111 and then say network 192.168.1.0.0.0.255 area 0 and then I'm gonna advertise 192 or you can say network 192.168.2.0 in 0.0.0.255 area number. Okay, I did the wrong thing. So I needed to advertise 1.0 into area 10, right? So I remove that particular route by using no command. Yeah. So I remove that route and I will advertise it by using area number 10. And then I will advertise this particular route, which is 2.0 in area number 0. There. That's the correct way of implementing it, right? So that's what we need to do over here on R1. Then I'll go on R3 and do the same thing, that advertise 6.0 into area number 20 and 3.0 into area number 0 again. So there you go. On this is our R2, that's our R3. So over here I'm gonna say router OSPF3, router ID 3333, and then I say network 192.168.3.0.0.0.355 or 255 and then area 20. Oh sorry, area 0 and then network 192.168.6.0 area 20. Correct? That's how the configuration needs to be done on R3. So both of the networks are advertised into their respective areas. Then I'm go on to the middle router, which is R2. And then over here, I'm gonna advertise both the routes that I have, or both the networks that I have, as part of area 0. So I say router OSPF2, router ID 2222, network 192.168.2.0.0.0.255 area 0, and then 192. There you go. And then I say 3.0, and there will be another OSPF adjacency 192.168.3.0. There you go. Another neighbor came up. Makes sense? And you can check that by saying do show IP OSPF neighbor. There you go. You have two neighbors over here. And if we check now that whether the communication, because if I look at the routing table over here, do show IP route. There you go. You have received a route update that is 192.168.1.0. Okay, there seems to be some misconfiguration on R1, but on R2, if I look at the routing table, the routes that you actually receive from different area will be tagged as OIA, which means OSPF route that is received from inter area. So the routes that you receive from different area is called as inter area routes. Okay, and the route that you just receive from the same area will be treated as normal OSPF route. But in our scenario, for this particular second router, the route which is 1.0 should have been an inter-area route and not an intra-area route, because it's being received from area number 10. So I'm going to go on R1 and check in which area I have advertised it. You see that? I have advertised it correctly in the area 10, but let's check that. Do show run section router OSPF. And yeah, 2.0 is part of area 0 and 192.168.1.0 is part of area 10. Which is correct according to my knowledge. If I again check that do show IP route. Again, this route should have been an OSPF inter-area route, just like you have 6.0. Anyways, if I go on to the router number 1 and check the routing table, do show IP route. There you go. You have 192.168.3.0 that is treated as, so you should have had two inter-area routes there, which is 3.0 route and which is 6.0. Okay, yeah. But only 6.0 is being treated as inter-area route over here as well. If I go on to the last router, which is R3, and check do show IP route there, over here, none of the routes are being treated as inter-area routes. However, it has both 1.0 and 2.0 as the OSPF routes that are being received there. But you can see that IA, which you can see over here, IA stands for OSPF inter-area routes, and normal O stands for OSPF routes. This might be one of the bug over here that you see of the packet tracer, but originally you can treat it somewhere like in the middle router. Both the routes that would have been received from area number 10 and area number 20 should have been in inter-area routes. It's only showing 6.0 as the inter-area route and not showing 1.0 as inter-area route over here, but it should have been like that. So this is kind of a bug, I can say, of packet tracer. But originally, for making the concept clearer, the routes that you receive from different OSPF area are treated as OSPF inter-area routes, and they get highlighted with an IA tag along with the O tag. However, yeah, however, you can see if we check the communication, whether it's being made possible or not. If I send traffic from here to here, yeah, it's going successful. So the communication is being made successful over there. But again, it's just the highlighting of packets that how the routes are being treated. So that's kind of a bug in packet tracer, I can say. But so far, in order to understand how the concept works, this is what we had to check, that how backbone area, which is area 0, connects normal areas together and how it lets you communicate between multiple areas if your areas are also connected to the backbone area some or the other way. Do you understand that concept? Perfect. So go ahead, try this particular lab into your packet tracer as well and see if it works for you. Okay, let me know when you're done. Thank you. All right, guys, I believe you guys are done with the thing. And I believe you understand OSPF pretty well now. So far, that is needed in CCNA. So I would say that was actually all that we had to discuss in this particular session, and I hope you enjoyed the content. And we are pretty good with routing that we had to discuss. We discussed about all the protocols, even though in official CCNA curriculum, the RIP and EIGRP has been removed now, and there is just OSPF and static routing that is there. So, but in order to understand the importance and to understand OSPF, you actually need to have the knowledge of how RIP and EIGRP works so that you can compare it. And yeah, for the remaining sessions, however, I would like to notify you that we are just going to have another 2 sessions next week, because from the following week, which is like next to next week, I have an important assignment to take up. So the remaining part, which is switching, will be done in one class, and then access control list, network address translation, security, and automation will be discussed in another class. So probably we're gonna have an extended class in the next weekend, because we have just 2 sessions that I can afford in order to have with you guys, because I have something else that I have came up to in my schedule, and I cannot ignore that. So I hope you can understand that. However, we will extend the time of our session if it's needed. So yeah. So I believe that you have been that you enjoyed the session today, and I'd like to thank you for joining it. I'll see you guys next week, same time. Till then, do practice a bit, okay? Spend some time over there. Amar, I've received your email, but I've been busy throughout the day. So I'll look into it and I'll update to your email as soon as possible, okay? Because I'm busy in the weekdays as well and the weekends as well. So yeah, I'll update to you once I get time for that. Perfect. Yeah, that's correct, RJ. Packet tracer has a bug. It shouldn't behave like that. Okay. All right. Thank you, everyone. Take care of yourself. I'll see you guys next weekend. Till then, have a good weekend. Have a good weekday ahead. And yeah, thank you. Bye bye.